Okay, so I'm going to have a look at differentiation from first principles, and this is in the topic of calculus. So this is a video for those students in year 11 studying extension 2, or students in year 11 doing the advanced mathematics course or the old unit 3. Okay, so let's have a look at differentiation from first principles. So if we've got a curve, let's call this curve h of x, and we wish to find a formula for the gradient at any point along the curve. So with traditional numerical methods, we would draw a tangent to the curve. So this is our tangent here. And this is the curve h of x. Now calculus is a little bit more sophisticated than just drawing tangents to curves. We can derive a formula to find the gradient at any point along the curve, and we refer to the gradient, which is usually referred to as m, as dy dx, or if we're dealing with functions, f dash of x, or simply y dash. Okay, so all those things mean the same thing. So if we are differentiating from first principles, our goal is to derive a formula which gives us the derivative or the gradient at any point along the curve. And we're only differentiating smooth, continuous functions. Okay, so let's have a look at this. Okay, so let's define a function. Let's call our function f of x. So I'm just going to remind us of our old gradient formula. So let's say the old gradient formula is the change in the y coordinates over the change in the x coordinates. Okay, so let's choose one point on the curve. So let's choose this point f of x. Okay, so we know that the x coordinate of this is, okay, is going to be down here, and we call that just x. And if we go up to the curve, that is going to become f of x. For example, if we have x is equal to 2, and the graph is f of x equals x squared, well, our f of x value is 4, because 2 times 2 is 4. Okay, so let's travel h distance along the graph. So we're going to travel h distance along the graph, and we're going to arrive at x plus h. X plus h, having travelled h distance along the graph. Okay, h. So let's go up to our function f of x. Let's go in red. And that cuts the graph at f of x plus h. Okay, so using our old gradient formula then, let's find the gradient of that line. Let's put some straight lines in. Okay, so we're finding the gradient of this triangle here. Okay, so using my old formula, I'm going to get f of x plus h minus f of x all over x plus h minus x. Okay, so let's do some algebra there. I'm going to get f of x plus h minus f of x all over h. Now, what would happen if we could limit this h to 0? Limit it all the way to 0 and just get the gradient at a particular point. So we want to make h as small as we possibly can. Now, let's consider if we let h equal 0. Okay, so you can try that on your calculator. Do any number divided by 0 and you're going to get an error or an undefined message. We cannot divide by 0. So what we do instead is we take the limit of h as it approaches 0. So we write that as lim, standing for limit, h going all the way to 0 here. Okay, so just to recap, we said what happens if we make h as small as we possibly can to get the most accurate value at the point of f of x. And we said, well, we can't divide by h, so we're going to use the limit as h approaches to 0 to find the behavior or the value of the function as close to 0 as we can possibly get. Okay, so let's have a look at some examples. So differentiate y equals x squared from first principles. Okay, so not that it's going to help us, but we can draw the graph of y equals x squared. Let's do endpoints. Okay, so red. Okay, so the graph of y equals x squared is going to be nice, smooth parabola. Okay, so the first thing we do is write down the formula for differentiation from first principles. So f of x plus h minus f of x all over h. Okay, so let's write this down again. Limit h to 0. And we know for every value of x, we need to add h, subtract f of x, which is x squared, all over h. Okay, so let's start working this out then. Square the first, square the last, double the product, minus x squared, all over h. So let's see if we can get rid of some values. So the x squared goes, and we are left with limit h to 0, and we can factorize the remaining values to get 2x. So these cancel. And now we do our limit. We limit h to 0. Let's do that then. And then we are left with x squared, with 2x rather. Now let's write down what this actually means. So this means that the derivative, i.e. the gradient at any point along this line here, is going to be 2x. So let's try it out at 2 points. Let's try it at -1 and +2. Okay, so let's just use the dotted line style. Dotted. Okay, so let's do -1 and 2. Okay, so value there is x is equal to -1 and x is equal to 2. So the gradient at -1 is just simply 2 minus 1, -2. So the gradient at that point, if we can draw in a tangent, it's going to be -2. Let's see if we can find the, let's do that in green so we know what we're doing. Point there and a point there. Okay, so let's do f dash of 2. 2 times 2 is 4. So we get a negative gradient there and a positive gradient here. Okay, so let's look at y equals x squared plus x plus 1. Okay, so look at the different terminology. We have f of x, we define in a function, and this is just a graph. Here we have a function. We have our f dash x value as a function, and we're just given a graph here. A function and a graph are two different things, and I'll do a separate video to explain the definition of a function, but the function formula still works here. So we've got limit h to 0 plus h minus f of x all over h. Okay, so we must write down the limit each time. So we need to add on x, we need to add on h to each value of x. Let's do that then. We've got x plus h squared, x plus h plus 1 minus x squared plus x plus 1, close bracket, and divide all by h. Okay, so let's start our expansion. So we've got x squared plus 2xh plus h squared plus x plus h plus 1 minus x squared minus x minus 1 all over h. Okay, let's see if we can get rid of some variables. We can get rid of the x squared, get rid of the x, get rid of the 1. So we are now left with the limit of h to 0. We can factorize h out to get 2x plus h plus 1 all divided by h. So we can cancel a h there, and we're going to limit this h to 0, so we're left with 2x plus 1. So just to reiterate, this lovely expression here gives the formula of our gradient at any point on the curve. Okay, so we're going to try some more difficult questions here, and we're going to use some results of limits which you may not have done before. Okay, so let's have a look at the derivative of y equals e to the x from first principles. Now, this is just a quick note, and this is really important. We only use first principles if we're asked to in the question. So if it says differentiate e to the x, you would just use your normal way of differentiating. If it says from first principles, you must use first principles. Okay, so let's go. Let's make a start. Okay, so we've got f dash of x is the limit h to 0 of f of x plus h minus f of x all over h. Okay, so let's make a start. E of x plus h minus e of x all over h. So we can do some factorization here. We can take out e of x to give e of h minus 1 all over h. Now, this is our special result, which I just want to talk about. So we now need to find the limit of h to 0 of e to the h minus 1 over h. Okay, now there's a special rule in maths when finding limits. It's called L'Hopital. And that says that the limit of x to anything, let's call it a, is the same f of x, g of x, is the same as if we differentiate top and bottom. Okay, you don't need to know this result, but I just thought I'd show it to you. So if we differentiate top and bottom with respect to h, we get limit h to 0. We're just going to get e to the h over 1. Anything e to the 0 is just going to be 1. So we can rewrite this limit as 1. So let's do that then. Let's rewrite that limit as 1. Just do the right thing. So we can take out e to the x and find the limit of h is equal to 0, and we said e to the h minus 1 over h. That goes to 1. So we just simply left with e to the x multiplied by 1, which is just e to the x. Okay, so you can look up that result of L'Hopital. All L'Hopital says is that we can differentiate numerator and denominator, and the limits will be equal. Okay, so the last and final one is differentiate y equals sine x from first principles. Okay, so this is going to be much more difficult than you're likely to get in the exam, but I'll show you how to do it anyway. Okay, so let's use a different colour. Okay, so let's write down the formula for differentiation. H to 0, f of x plus h minus f of x all over h. Okay, so let's make a start. And this uses some results from some quite advanced trigonometry and rules of limits. Okay, so let's make a start then. So we got limit h to 0, and let's do sine x plus h minus sine of x all over h. Okay, so we can use our double angle formulae now to rewrite that as limit h to 0 sine x cos h plus cos x sine h minus sine of x, just put that right there, all over h. Okay, so we can factorize now. Stick the same color. Limit h to 0. So let's factorize then. Sine of x to get cos h. So we factorize in, let me do it in a different color. Factorize in from there and there. Cos h minus 1. And we are left with if we factorize plus this thing here, plus cos x sine h all over h. Okay, let me double check to see if that's right. Okay, fine. Brilliant. Okay, so using our rules of limits, we can rewrite these as separate limits. So let's do that then. I'm going to go to a new page. So we're going to get limit h to 0, and I'm going to rewrite each of the limits separately. So I've got sine x cos h minus 1 all over h plus the limit of h to 0 of our second part, which was cos x sine h all over h. Okay, so using rules of limits, we can factorize. We can take a sine x out, and we're going to be left with the limit h to 0 of cos h minus 1 over h, plus we can factorize here to take cos out, and we've got limit h going to 0 of sine h over h. Okay, now I'm going to use our special rule of L'Hopital. Okay, now I'm going to go in a little bit more detail this time. Now, L'Hopital's rule says that we can differentiate the numerator and denominator, and we will get the same limit. Okay. So let me just write this down. L'Hopital's rule says, okay, let's do this in red. L'Hopital's rule. L'Hopital's rule, and that says if we take a limit x to a, that is the same of f of x g of x. That is the same as taking the limit x to a of f dash and x dash. So here we've differentiated the numerator and denominator. We've differentiated the numerator and denominator. And I'm going to do that for each of these to show what we get rather. Okay, so using L'Hopital's rule on each of these, I'm going to show the result. Okay, so let's limit h to 0, and I'm going to differentiate top and bottom with respect to h. Okay, so the derivative of sine is cos, and the derivative of cos is minus sine. So we get minus sine h. The 1 goes, and we just left with 1. Okay, so we can now do sine of 0. On your calculators, you can all see that the sine of 0 is just simply 0. Okay, so all this goes to 0. So let's do this limit. So we've done this one. Let's do this one. We've got limit of h to 0, and we're going to differentiate numerator and denominator. So we differentiate sine h to get cos h, we're just left with 1. So we can do cos of 0, which is 1. So here we just left with 1. So let's finish off doing f dash of x. So we've got 0 times sine x plus 1 multiplied by cos x. Well, 0 times anything is 0. 1 times cos x is just cos x. So the derivative of sine x is cos x, and we've shown that through differentiation from first principles. I hope you understood that, and carry on doing your maths. Bye.